My name is Androwski Spicer. I'm a solution architect with Amazon Web Services, and I've been a solution architect with Amazon Web Services for almost 3 years. Now, as you're aware, I will be presenting on evolving VPC design. When I started creating this deck, and I saw the services that we had planned to launch this reInvent, one theme kept on coming back to me, and that was simplification. Now, this is the 5th year that we're actually doing this talk. So can I see a raise of hands of those who have actually attended this session before? Welcome back. Well, this year, my plan is to introduce you guys to solutions and ways of implementing network architecture for one VPC or hundreds of VPCs across multiple geographic regions in a very easy and simple way. Now, this is actually a 300 level talk. It's an advanced talk. So I don't spend a lot of time walking through what a VPC actually is, nor do I define an internet gateway, virtual private gateway, or speak about VPC endpoint at the basic level. So I trust that you know what all these components are within the VPC. For those of you who actually aren't familiar with what the VPC is, there are 2 talks that you can actually look at. Net 201, which gives you a really good overview of what an Amazon VPC is and the different components. And also Net 301, which really dives into how do you extend your data center into AWS. We all start here. One VPC, a set of applications. Eventually, we end up here with hundreds of VPCs spread across multiple Amazon geographic regions across the world. And the questions that we ask ourselves is, how do we reduce latency between our data center, our users, and these different environments? We also ask the question, how do we simplify routing? How do we relieve that pressure from our network engineers and our network team? And this talk aims to answer that. So let's talk a little bit about VPC design. When you set out to create a VPC, the very first question you ask yourself is, where am I going to create it? The answer is normally driven by, where are my customers located? Or do I have to satisfy data sovereignty laws? Does my data need to reside in a specific geographic area? The second question you generally ask yourself is, how many IP addresses do I actually need? In the beginning, it might just be 10. But sometimes there's no way for us to gauge growth. There's no way for us to actually look into the future and say, how many IP addresses am I actually going to need? What exactly is going to run within this environment that I have not thought about that doesn't exist within my own data center? So what we recommend is to go as big as you can. And as big as you can is a /16 CIDR notation, which provides you, as most of you know, with over 65,000 IP addresses. 65,536 to be exact. If you don't need that much, we still recommend it, but you have the option to define CIDR notations much smaller than that. The smallest you can define is a /28, which gives you around 16 IP addresses, 5 of which are usable. So let's look a little bit at how you should actually design your IPv4 space. Before you implement anything, I personally recommend speaking with your network engineer if you're not a part of that team. The reason is, fundamental networking principle of overlapping IP address space and how you handle that still exists. So in order to prevent you from redesigning an environment once it's up and running, I recommend speaking with your network team, find out what IP address spaces you can actually use within AWS, because one of the things you think about when creating a VPC is what networks it actually connects to. Once you define the networks it's connected to, once you've gotten all of this information from your network team, then you go ahead and create your VPC. IPv4, by default, is required, but you can optionally add an IPv6 CIDR block to your AWS environment for a specific VPC, and that falls under your VPC ID. The thing with these IP addresses are they aren't linked local addresses. These are global unicast addresses, which means by default, they're globally accessible from anywhere in the world. You might be asking yourself the question, how do I then secure my resources to prevent from anyone online who isn't authorized to access my environment from doing so? And I'll talk a lot about that later on. One thing to note, AWS actually defined that CIDR block for you. So when you activate that IPv6 space, we give you a CIDR block. We give you a set of IP addresses that you can actually use. It's a /56, which gives you about 18 sextillion IP addresses, and you can subdivide that into /64s as you need it. Now, in the beginning, I said, go as big as you can. What happens if you go as large as you can, or you started out with a very small VPC? How do you then grow? In the past, you had to jump through a few hoops, create other VPCs, create pairing relationships between those VPCs, or simply do away with that initial VPC and rebuild the environment. Nobody wants that. So go as big as you can to reduce creation time. But if you go as big as you can and you need more IP addresses, you can leverage VPC resizing. VPC resizing does not mean changing the CIDR notation. It simply means adding an additional CIDR block to your VPC. And the CIDR block can be as large as a /16 as your primary VPC, or as small as a /6/28. And you have the option of adding one or multiple. By default, you can add 5. You can actually have 5 total CIDR blocks under one VPC ID, but you can actually raise this soft limit. Things to note, in your route table, if you guys are familiar with the AWS environment, which you should, your route table would actually have a local route for the additional CIDR block that you just add, further extending the flat network that you know AWS VPC to be. Another thing to take into consideration is what we spoke about earlier. You can't have an overlapping IP address space. You must think about all the networks you plan to connect to, because, for example, if you have an overlapping IP address space and you plan to pair with another VPC, that VPC connection will never be established. Another thing that's very important for you to know is that your primary CIDR block, unlike the additional CIDR blocks, cannot be changed, but you can remove CIDR blocks as you don't need them. So if I add 5 CIDR blocks and I no longer want one, I can remove it, but my primary can never change. Now, your CIDR notation, the IP address space for your primary VPC, actually dictates what IP addresses or what CIDR blocks you can actually add as a secondary. So if I have a 10/8 and I decide to add a 172.16/12, you can't do that. You can only add a IP space that falls within the 10/8 network. Okay, so we've created our VPC. The next question you ask yourself is, how do I go about creating subnets? Not only that, how do I distribute my subnets? What are my options? Well, within AWS, we believe in distributing your IP address space across all availability zones. Doing this gives you the ability to create environments that are fault tolerant and highly available. So if I'm evenly distributing my IP address space, what does that actually mean and what does it actually look like? It should never look like this, right? I mean, this is a management nightmare for your network team. Nobody wants that, right? The thing about this is how you define a subnet. Within a traditional network, a subnet was an isolation container for applications. Within AWS, that switching limitation does not exist. So a subnet is redefined, and you isolate your applications using stateful firewalls and stateless firewalls. And you also group your resources using tags. Tags are very important. Within AWS, you can actually find out how much a specific project is costing you based on the tags that you assign to the different resources. You can easily identify your resources, and this comes in very handy, especially for auditors. And you go into the environment and you want to know what something is, ensure it's tagged. So, what do we recommend? We recommend treating a subnet as a container for routing policies. So, instead of using a subnet to isolate applications, I think about what does my application need to interact with? Does this application interact with users online? Should my users have the ability to actually initiate communication with my application? Does this application only need to communicate back on premises, which means I may not need the internet at all? So by answering those questions, you define public subnets, which has applications in which users and resources online can initiate communication with your applications in your VPC. You have hybrid subnets. And hybrid subnet is one in which you have applications that no one online should initiate communication with, but your application need access to the internet for certain resources. And lastly, you can have private subnets. And private subnets have no way of getting to the internet. As a matter of fact, the only thing they communicate with are applications within the VPC and on premises. Now you might be asking yourself the question, if they communicate on premises, how do they actually do it? If I'm creating an IPsec VPN tunnel, am I not going through the internet? And we'll talk about that later on. Now, your IPv6 space should look similar. Public subnet and private subnet. I said before, however, that an IPv6 space is globally unique and accessible by default. How do you make that private? And I'll answer that in this section. But first, let's take a look at routing within your VPC. Your VPC, regardless of how many CIDR blocks you've added to it, is a flat network. By default, everything has the ability to communicate with everything. You isolate your traffic using stateful and stateless firewalls. So security group and NACLs. NACLs operate at the subnet layer. Security groups are directly attached to your EC2 instances. Within your route table, there's a route added there for you by AWS that you can't modify, change, or remove. Now, when you create a subnet within AWS, there's an implicit association. There's an implicit association with a route table, which is the main route table. Now, this route table contains all the routing policies and all the routing definitions for you to get to wherever you need to get to, just like your Cisco routers on premises, just like any other router that you have. So how then do I make a subnet public? The answer is, a subnet is actually made public when you add an internet gateway to the route table in which that particular subnet is associated with. How do you then get to the internet? Is that the only thing I need to do? The answer is no. In order for you to communicate directly to the internet gateway, the resources in that public subnet must have either a statically assigned or dynamically assigned public IP address. The internet gateway takes care of the NATing. It remembers what public IP address was allocated to what instance and does it NATing intrinsically for you. And within your route table, you'll have a default route going to your internet gateway for your public subnet. What does it look like for your IPv6 space? The only difference with IPv6 is there's no NATing needed, right? I mean, these addresses are globally accessible by default. So the concern is not how do I get to the internet from my internet gateway, it's how do I actually prevent unsolicited traffic. You prevent unsolicited traffic by leveraging a unique internet gateway, which is the egress-only internet gateway. You can create that, and you can add it to your route table, and Amazon recognizes that device as a target for internet destinations. Now, the routing policies for your IPv6 space are treated differently from your IPv4 space, which means that the limits that exist on IPv6 for adding routes to your route table are not affected by the limits that exist for IPv4. So if the limit is 50 for defined routing policies within a route table for IPv4, IPv6 has 50 for itself as well. So what about these two subnets? Hybrid and private. Hybrid is a combination of private and public. By default, some of your applications that need to initiate communication to the internet may also need to communicate with applications on premises. So what you'll find in that row table, especially for the private, or for the private only, is not an internet gateway, but a virtual gateway. And the virtual gateway is a VPN concentrator. That's where all your VPN connections come into, whether from your data center or remote offices. And it can actually be treated as a VPN hub, where you have multiple VPNs from across the world, all terminating here, and routes being issued from your row table that is connected to. Once upon a time, the only option for one connectivity was Direct Connect, that provides point-to-point communication between your VPC environment and your data center. That BGP session in negotiation is handled differently today based on announcement that happened at reInvent. And we'll talk a lot more about how that simplifies not only routing, but actually connecting multiple VPCs from across the world. So I have a VGW, a virtual private gateway, in my row table. How then does my hybrid subnet access the internet? Simply put, it accesses the internet by adding a NAT device to the row table specifically for your hybrid subnet. Your hybrid subnet has its own row table separate and apart from your private subnets. Within AWS, you have the ability to create multiple row tables and attach them to subnets as you see fit. So you can create a NAT device, which in this case is a NAT instance, and a NAT instance is simply EC2 instance that you configure for NATing. That's really what it is. The problem with this solution is it provides management overhead. It introduces complexity. You have to now decide, how do I actually create high availability for my NAT instance, because it's very important, right? If it goes down, how do I move traffic from that instance to another? What we've done to simplify that for you is to create the NAT gateway, as most of you are aware. And the NAT gateway isn't a single infrastructure. It's actually a set of horizontally scaled infrastructure that you don't manage at all. All you do is allocate it to your account. That's it. Now, to allocate a NAT gateway, or to create a NAT gateway, you first choose the subnet in which this NAT gateway is going to live, and then attach an elastic IP address or a static public IP address to the NAT gateway. It lives within a single geographic region. Well, it lives within a single data center, right? The problem with that is, if something happens where that data center goes away, then you're flat in the water, right? You can't route anything to the internet. So what we recommend to overcome that challenge, but also the challenge of, what if I have a NAT gateway, right? And I exhaust the bandwidth available to it, which is 10 gigabit per second, because I have 120,000 applications all going to the internet to serve my customers. What then do I do? What we recommend is not to have one NAT gateway, but to have multiple NAT gateways spread across your availability zones in which your resources live. And that way, we're zoning our internet traffic. There's no traffic going across your availability zones to get to a specific area to go to the internet. Everything happens within its own specific data centers, which also speeds up how quickly you respond to your customers. So, how do I secure this NAT gateway? First, you can't secure a NAT gateway using a security group, or what we call a stateful firewall. What you do is to actually create policies within your network access control list that operates at a subnet layer where your NAT gateway really lives, right? Because it lives within your subnet. So you can then create policies that protects your NAT gateway from subnets that should have no access to it. So after doing that, another way that you can actually protect it is by simply saying, you know what? I'm just not going to add a NAT gateway as a destination, as a target for any destination on the internet. So your route tables have no NAT infrastructure at all defined. So you might be asking yourself the question, or I hope you're asking yourself the question, under what circumstances don't I use a NAT gateway? Right? And there are just a few. The first is, if you have destinations online that you know are actually going to respond with fragmented TCP communication, then NAT gateway doesn't actually provide or support IP fragmentation. So you may not want to use a NAT gateway for specific traffic like that. You may want to instantiate a NAT instance and use that instead. Also, a NAT gateway supports 65,000 simultaneous connections. So if you have more than that going to your NAT gateway, then you may want to create multiple NAT gateways or use something else. So where are we? Where we are is that we have one VPC. We have ways to get to the internet. We have ways to get back to our corporate network. So is that the only thing that AWS provides for communicating? What about services like S3, DynamoDB, Kinesis, right, Lambda? How do I actually get to these applications easily and through the Amazon network, not through my internet gateway? Well, I'm going to talk about that. But before I get there, there's one design that not a lot of people talk about, and that's ingress. Am I going to attach a public IP address to all my instances? Do I have to really do that? Right? How do I simplify, ingress points for my customers? Well, Amazon has made it really easy to do that. We've created a set of load balancers within the Elastic Load Balancing portfolio. The first we started with was a classic load balancer, or the CLB, and the CLB operates really at layer 4 with certain layer 7 functionality. The second we created was the application load balancer, because customers need the ability to not only inspect packets, but also integrate with other security appliances like WAF, or a web application firewall service, that simplifies and reduces your time to market, which is why we're here, right? Which is why the cloud is here. The last one we created, which was released recently, is a network load balancer, which also operates at layer 4. You might be asking yourself, classic, network, both layer 4, why is it necessary? Well, the network load balancer is actually much different from the CLB, or the classic load balancer, in that by default, it's built to handle millions of requests per second. You don't have to pre-warm it to get there. It does it natively. Not only that, it maintains the client source information and passes that along to your application. So what about my on-premises network? What if I have my applications running on-premises, but I want to easily migrate to AWS because I've rebuilt my infrastructure inside AWS, but I want no downtime? The network load balancer is especially poised to do that, because once upon a time, you could only attach instances to a load balancer based on instance ID. The network load balancer handles that differently. Another feature that network load balancer has is the ability to zone your traffic. Just like your NAT gateway, where you don't want cross AZ or cross availability zone communication. You want all communication to reside in one single set of data centers. The network load balancer does that easily. So when you create a network load balancer, you specify the availability zones that you want your applications to run in and where you want load balancer to live. And we create a load balancer for you. Not really. We allow you to create network interfaces. So you create a network interface that acts as an entry point for communication to the load balancing nodes, right? The network interfaces come with a private IP address. And if your network load balancer needs to communicate online, you can create your own elastic IP and attach that to the network interface. So you know exactly what your IP address is, and this IP address will not change. It makes it easy for you to update your firewalls using IP addresses, right? Once you've created your network load balancing nodes, you then have to attach instances to it. We just said that you can attach an instance using the instance ID, or you can attach it using the IP address of the instance itself, which means that I can actually pair my VPCs and attach instances in other areas to my network load balancer, right? It gives you a myriad of options. Now, to attach an EC2 instance to your network load balancer, you do it by creating a target group and attach your EC2 instances to the target group. The network load balancer then routes traffic to the target group based on certain criteria. If resources in the availability zone that you run your applications in fail and you have a second availability zone, Amazon will move that traffic over to the availability zone that's available for you. The IP address is also removed from the hostname within Route 53. So, how does it work? You create listeners, which, for example, use port 443, network load balancer. The network load balancer only supports TCP. That's very important to remember. It doesn't support UDP at this time. So you create a listener, and this listener maps to a rule. And this rule determines which target group to route that traffic. So if I have applications on port 443, and I have applications on port 80, it may go to two different set of EC2 instances, or different ports on one EC2 instance itself. Am I stuck with just virtual machines? Can I run containers? Yes. Network load balancers are specially poised for that. Now, we've spoken about this. So let's look at a real-world use case, something that lots of people do on a daily basis. If I actually want to implement a proxy farm, let's say you're using Squid, right? Squid proxy farm. But, I don't want to manage the availability of that farm via the access point. What do I mean by that? I want something to actually load balance my traffic, but I also want the ability to specify in my route table what that is. I don't want to specify an EC2 instance because I don't want to manage EC2 instances, right? I simply want to think about my proxy farm and if they're available. The thing about that is I don't necessarily have to manage my proxy farm because I can put it inside of an auto-scaling group, right? If one machine fails, it's recreated. I don't even have to know, right? I know it's always available. I know my environment is always fault tolerant. So the network load balancer gives you the ability to front-end your proxy farm with itself and then specify the network interface that you created inside your route table. Right? What that gives it the ability to do is not think about putting a proxy in front of a proxy for availability. Make sense? Okay. So your internal apps would route traffic to your ENI, and then that traffic goes to your network load balancer and get distributed across your Squid farm. Now, I want you guys to remember this slide because I'm going to build up on it as we go along. So let's talk about egress control. More and more, we build applications to interact with AWS, public AWS services. Once upon a time, customers, did this, for example. I mean, you could do this. We don't recommend it, right? What we recommend instead is to do this. We recommend leveraging AWS VPC endpoints. Most of you are familiar with the gateway VPC endpoint. You also have the ability to leverage a new type of endpoint. Sorry, too fast. A new type of endpoint, which we call the interface endpoint. These two endpoint services are extremely different. With the gateway endpoint, you have access to services like S3 and DYNAMODB primarily. With the interface endpoint, you have access to services like Kinesis, Service Catalog, Elastic Load Balancing, EC2 APIs, you name it. Now, for those of you who are familiar with endpoints, these are just like your NAT gateway or horizontally scaled infrastructure that you don't manage. It gives you the ability to route traffic privately to the AWS public service environment without going through your direct connect, your VPN tunnels, or an internet gateway or any NAT infrastructure at all. So your traffic remains within the AWS network. Let's take a look at the gateway VPC endpoints. Now, when you create a gateway VPC endpoint, the request by default goes to the VPC endpoint prefix list that's defined within your route table. when you create a VPC endpoint, you specify the VPC, you specify the route table to associate with that VPC. Once the endpoint is created, we add a route to your route table that can't be modified or changed. That's a very specific route. The prefix list actually front ends the entire IP address space for the public service that you're trying to interact with. We did this specifically because that IP address space changes when we don't want you to have the overhead of always checking to see what the IP address space is and changing the route within your route table. So we simplify that by creating the gateway endpoint for you and giving you access to a prefix list. Another thing that you think about when you create a gateway endpoint is, not this, how do I secure it? How do I secure my endpoint? Well, there are multiple ways. The first I'll discuss with you is your security group. You can create outgoing security group rules that sends traffic specifically to the prefix list ID of your VPC endpoint. So what happens if I have resources in my private subnet that only needs to communicate on premises, but also have access to AWS services like S3 to get data, all right? I don't necessarily want to add a NAT gateway to my route table. I want that traffic to be private. I'd leverage a VPC gateway endpoint and add routes to the firewall or the stateful firewall that exists for that application or set of EC2 instances. And this is what it would really look like. The second way of controlling access is using identity and access management. Today, you create IAM policies for users, roles, groups, etc. Right? Within these policies, you specify what resources this user can actually access and what API call they can make when accessing these resources. We give you the added ability to specify the VPC endpoint ID when actually accessing services like S3 or DynamoDB. But what about specifically S3? Can I use S3 bucket policies? Yes. What you can't do is actually specify the IP address within the condition statement of the bucket policy to say, I'm only going to allow access from this VPC and this VPC IP address. You can't do that. Instead, associate a route table with the gateway that has a subnet that should only access that specific gateway in the manner in which you want that to be accessed. What do I mean by that? And let's use DynamoDB as an example. I can create a VPC endpoint policy that says all traffic going through this endpoint only has access to a specific bucket, or in the case of DynamoDB, a specific table. All other traffic are denied. And as you can see there, within the resource ID, I have the table identified. The last way that you can control access is by deciding which route tables to associate with my endpoint, right? I mean, if you shouldn't have access, then you will not be associated with my endpoint. All right, let's talk about interface endpoints. What is the difference between a gateway endpoint and an interface endpoint? The difference is the gateway endpoint has policies within your route table and sits on the edge of your VPC. So it has 1 foot inside your VPC and 1 foot in the broader AWS network. What we've done to simplify that by leveraging Amazon private links is we allow you to create elastic network interfaces inside subnets within your VPC, taking the service really from the public realm and making that public service a part of your VPC. How it works, this elastic network interface would be defined in a subnet that you have resources that should access the particular service. So, for example, if I need to communicate with Kinesis, right, I specify a specific subnet, we create the interface inside that subnet, attach a private IP address to it. But what about routing? What actually happens? Now, when you create an interface endpoint, you don't specify a route, nor is a route specified for you inside your route table, because your traffic is handled as a local route. Remember that flat network? It's now just communicating amongst nodes within your VPC. If you look inside your route table, it will not have a specific route to your ENI. What you do instead is use the endpoint URL to communicate with the service that you need to get to. So within your application, you specify the endpoint URL as the destination for what you're trying to do. And then we route that traffic as if you're actually routing traffic between nodes within your VPC or servers within your VPC. So when creating a VPC endpoint, you specify first the VPC ID of the VPC that you're creating this endpoint in. You then specify the subnet ID and the service that you're trying to interact with. Now, I would actually recommend running a describe endpoint request to see what actual availability zones that this service resides in. Because within AWS, all AWS services may not reside across all availability zones, and you want to know where exactly I need to create my Elastic Network interface to reach a specific service. Now, unlike the gateway endpoint, you don't specify an endpoint policy for your endpoint. What that means is your endpoints give you full access to the service, and control is basically based on what resource is trying to access that service. So whatever IAM policy exists for your user, or whatever IAM policy exists within the role that you're trying to, that you've attached to your EC2 instances, is what is actually analyzed, not an endpoint policy. One thing to note, very important, endpoints supports TCP only. So again, you specify your VPC, you specify the subnet in which your endpoints are going to be created, and you specify the security group that protects your endpoint. Your endpoint is protected using Amazon Security Group. So when you create your VPC endpoint, what is actually generated? We generate a set of endpoint host names. The first is what we call a regional DNS name. That's where you can specify that regional DNS name, and you don't have to worry about which availability zone your resources are in, because they'll communicate with that VPC endpoint URL, and then your traffic is routed to an ENI. We also allow you to zone your traffic. So if you have EC2 instances that are running in multiple availability zones, and you want no cross availability zone latency or no cross availability zone connectivity that comes with a cost, you can actually use specific endpoint URL for the AZ in which you reside or live. If you've attached a private hosted zone to your VPC within Route 53, then you can leverage the global or the service, public service endpoint URL, or service URL, not endpoint URL. And this will actually map back to the Elastic Network interfaces and the private IP addresses that you've allocated to your Elastic Network interfaces for your endpoint. You can also communicate with your service based on the IP address of the Elastic Network interface, which means you can also create records within Route 53 that maps back to the IP address. So you can create A records, really. So your own record sets. Things to consider. Endpoints are region specific. If you create an endpoint within US West 2, which is Oregon, US East 1, which is Northern Virginia, can't communicate with that endpoint. Another thing to actually identify is an endpoint is accessible via your direct connect. So if I have users' applications within my data center, they can actually communicate with my endpoint via direct connect, but they can't communicate with my endpoint via an IPsec tunnel between my virtual private gateway and my customer gateway or firewall or Cisco ASR or ISR series routers, etc. So as I stated before, I can specify within my security groups what subnets should be able to access my endpoints. So, give this side of the room some love. What about my services? We're talking about AWS services specifically, but what about my services? Can I create VPC endpoints for my Squid proxy farm within a specific VPC and allow another VPC owned by me or not owned by me to be accessed? Yes, you can. You most definitely can do that today. We have now taken the endpoint service and given you control over that. And saying to you, if you feel like creating endpoints for specific services or applications that you're running, go ahead and do so. And advertise or whitelist accounts, IAM users that should actually have access to that endpoint. And I'm going to talk about specifically what it does. But as you can imagine, endpoints created by you, which we're calling VPC endpoint services, has two components, the publisher and the consumer. The publisher actually has the ability to create an endpoint, create an application, put it behind a network load balancer, add that as an endpoint service within AWS, and then advertise or whitelist specific accounts and users that can actually access it. So when you create your application is behind a network load balancer, which is very important, by the way. This cannot exist without a network load balancer. It has to be behind a network load balancer. Remember, a network load balancer only supports TCP. It's very important. Once you've created your endpoint service, you can actually use the described endpoint service calls to find out if an endpoint service is available to me. Because I don't only have the ability to do that, right? Partners of AWS can create endpoints for their services. Let's use Salesforce as an example. What if I have a Salesforce environment and Salesforce says, okay, I want you to access this privately. They can create endpoints, endpoint service, give you access to it, and know you're accessing that environment via the AWS network only. So you're not going through direct connect, you're not going through the internet to get to it anymore. And once endpoints are advertised to you, you create interface endpoints to get to it. We spoke about that. So graphically, this is what it looks like. Your EC2 instances, your services, your containers, whatever it is, resides behind a network load balancer. The network load balancer is attached as the entry point for your service. And other VPC environments access that environment via the network load balancer. We spoke about these. So we're moving on from one VPC, and we're talking now about an environment that has hundreds of VPC, or tens of VPC, or 2 VPCs. So the first question is, why not one big VPC? Right? Why do I need multiple VPCs? Can't I just have one VPC and subnet it? I have the ability to add multiple CIDR blocks. Why not? That segues into why not one account? Why have multiple accounts? The answer for that question is an account is simply a container for API limits. So to answer that question extendedly, and to speak about VPCs as well, if I have an account that has production, I do not recommend having dev within that account either, because dev might exceed the API limits that impacts production and brings down your production network. So that's the reason for having multiple accounts. VPCs, on the other hand, the more VPCs you have, or the more stringent and deep your IAM policies will have to be to protect against cross-access. So one person or one server shouldn't have access to my other VPC. It takes time for your security team to do that. So you may want to consider having multiple accounts, multiple VPCs within those accounts. Another reason for having multiple VPCs is compliance needs, or multiple accounts as well. It's compliance needs, right? If I have a HIPAA compliant workload, I don't want everybody to have access to that account, right? If I have PCI requirements, I don't want everybody to have access to that account. I may just want to have my applications for that in its own account and build the infrastructure around that. Some companies decide to have multiple accounts based on departments because it's easier for them to identify cost centers. A very important reason to have a demarcation between VPCs and accounts is production and DR. Right. My DR should never be within the same VPC as my production environment. Right. Because it's ideally, that's in the same region. So if something happens in that region, my entire environment is down. So if I have multiple VPCs, all these VPCs have IPsec tunnels back into my office, right, my data center. I then have what can be sometimes hundreds of IPsec tunnels coming into my network. That, like having hundreds of subnets, is a management overhead and a management nightmare. Before speaking about that, let's really look at what happens when you create an IPsec tunnel within AWS. Now, when you create a VGW, Amazon today gives you the ability to specify your own private ASN. You can create multiple IPsec tunnels between the VGW and your customer gateway. That's default, by the way, specifically because we believe in high availability. Once these tunnels are created, we also recommend creating tunnels to a secondary or redundant device within your network. So ideally, at the end of this process, for one single VPC, you have 4 tunnels, right? If you have 100 VPCs, that's 400 tunnels. So we need to simplify that. Oh, by the way, when you create IPsec tunnels, you have the ability to use BGP or static routes. We always recommend BGP. With static routes, there are a few more steps in order to get your routes into your route table, besides propagating that route. BGP has the ability to identify a path that's down and move to another tunnel. So always BGP. So how do we simplify this? We simplify this by creating a central point and connecting all your other VPCs into this central point. And from that central VPC, an IPsec tunnel is created, or direct connect is created between your data center and that one central VPC. You have options. Today, you can use peering between multiple VPCs and that central point to allow for communication. So let's think about that, though. If I have an IPsec tunnel via my VGW to my edge router or my customer gateway, right? How do I then have transitive routing between multiple peered VPCs and my on-premises network? By default, Amazon VPC peering does not provide transitive routes. So I must add a mechanism to my VPC to allow for these attached VPCs or spoke VPCs to have access to my environment on premises. For those of you who aren't familiar with VPC peering is really a logical connection between one VPC and another VPC, really joining those VPCs to further form a flat network. Once you've done that VPC peer, that is, once you've sent a request to a specific VPC, and the VPC accepts that request, which is a manual process, then a VPC peering connection exists. In order to actually send traffic across that VPC peering connection, you have to define routes within your route table, within both route tables to reach each other. And this is what the route tables really look like. So if 10.222.2.0 needs to reach 10.111.0, then a route must exist for 10.111 within .222.0 route table. And what's actually specified is the actual VPC peering endpoint. You can't do transitive routing between two VPCs and another network, which means if I have three VPCs paired, A is paired with B, and A is also paired with C, B can't reach C through A. VPC peering also supports IPv6. We will talk a little bit later on about what it doesn't support. Now, in order for you to actually reach your on-premises network or reach other services like AWS public services that doesn't have an endpoint, you can do so via a proxy farm. Now, that proxy farm can be front-ended by a network load balancer today, as we spoke about earlier. Okay, good. So VPC peering can be done, but that's all within one region, right? What about my VPCs that exist in multiple regions globally? How do I connect those to this central endpoint to get back to my network? You can do this via inter-region VPC peering. Inter-region VPC peering gives you the ability to create a peered connection between a VPC in Oregon or US West 2 and Ireland. I've actually done this, and the latency is 139 milliseconds with no drop packets for a continuous ping for about 10 minutes. So that simplifies how I actually now connect to another region. I no longer have to actually create a Cisco router, a Palo Alto device, and then create IPsec tunnels via that and other VPCs in multiple other regions, which means I'm removing things I need to manage and using native AWS services to get there. Something else to actually note is I don't have to actually worry about encryption. Inter-region VPC peering, everything is encrypted by default for you. The limitations still exist, however, the limitation still exists of transitive routing, right? So how do we fix that? How do we solve for that? How do we simplify that, right? I may not want to associate one VPC with my data center, right? How do I get from Ireland, Singapore, to my data center? Do I always have to do transitive routing here? Well, not transitive routing, but do I always have to go through a proxy farm within my shared services VPC to get back to my data center that's located within Oregon? How do I simplify that? Do I then create IPsec tunnels? Before I get there are a few things that you need to know that differs drastically from local or regional VPC peering. One of which is you can't reference a security group for a set of EC2 instances across an inter-region VPC pair. Nor can you do a DNS resolution to a private IP address for a public host within your VPC in another region. It doesn't support IPv6. Sorry, it supports IPv6, that's a mistake. But it doesn't support frames, jumbo frames. So, before we talk about simplification of multiple VPCs connecting back to my data center, what about private links? Can private links replace peering to create that shared services hub? Yes. You can actually leverage Amazon private links to create that shared services hub and then advertise that particular application as a service to all your other VPCs. you've removed the need for VPC peering. Because once you introduce VPC peering, you have to think about security groups and you have to think about how do you make it secure. Because VPC peering basically says this network is now joined to this network and I can route traffic as if they're the same network. So private links simplifies that for you because the shared services VPC can't initiate traffic to VPCs that are attached, that are communicating to it. It's only there as an entry point, right? Further simplifying your life. Again, you can't communicate with your service via a VPN connection between your VGW and your local on-premises network, but you can do it via Direct Connect. So let's look again at that model incorporating inter-region VPC peering. So you can actually have private links advertising to VPCs in the same region, and then create a shared services VPC in another region that's basically allowing replication of data across that inter-region VPC peered link. So VPCs in another region aren't all paired with my central shared VPC hub. It has its own shared VPC environment. And I'm replicating data across both environments via Amazon inter-region pairing. And for Ireland, I can then create create a VPC endpoint service and advertise my shared environment as just a VPC endpoint service to other VPCs within that region. So I'm localizing everything now to each region, but I'm replicating across my inter-region VPC paired link. I'm simplifying routing, and I'm reducing significantly the time it takes for me to implement this. So let's answer that question. How do I simplify connecting my data center across the world? Once upon a time, we would recommend that you do this. And you still can do this. However, you may want to do this instead. If you look at the difference between both diagrams, I have removed the MPLS, the need to backhaul your traffic via your MPLS network to get back to your data center. What you do instead is create an Amazon Direct Connect gateway. Creating an Amazon Direct Connect gateway gives you the ability to create that BGP session between your on-premises network and an Amazon gateway, and then associate all your VPCs with the Amazon Direct Connect gateway, whether they're located in the same region or globally. And the good thing is, we've already answered the question around how do I connect my VPCs together? Because my Amazon Direct Connect gateway only connects my VPCs to my on-premises data center. Let's look a bit deeper at Amazon Direct Connect gateway. But to do that, let's define it. An Amazon Direct Connect gateway is a global object. When you create it, it doesn't reside in a specific Amazon geographic region. You can access this VPC gateway across the world, right? And it allows you to create virtual private interfaces, very important, not public interfaces, virtual private interfaces between your network and the Amazon VPC network. By default, you can create 200 Direct Connect gateways, and you can attach 30 virtual private interfaces per gateway. And you can associate 10 VGWs to this gateway. These are soft limits. So you can apply to AWS and we'll up those limits for you, depending on what your needs are. So let's look at the traditional way of connecting VPCs together. Your VPC to your network. Once upon a time, you had to create a private virtual interface to all the VPCs that you wanted to communicate with. Right? So if you had 4 VPCs, that's 4 times you're configuring private virtual interfaces to your network. Right? Which means if it takes you 15 minutes, it now takes you an hour. If you have 100 VPCs, what does that look like? Right? What we've done is to remove that complexity. Configure it once and associate once. What it means is when you implement Direct Connect and you're creating a private virtual interface, you now create a private virtual interface between your network and the Direct Connect gateway. It's no longer between your network and the virtual private gateway of the VPC you're trying to connect to. You still have that option, all right? But for all the VPCs within your account or within a single account, you can create a Direct Connect gateway, associate all those VPCs with that gateway, and now you can communicate with your VPCs via your on-premises network, significantly reducing your time to market. So, what does routing look like? Now, the BGP session that's actually established is between your edge device and the gateway. The routes that you advertise over into that gateway is then taken and sent into all the VPCs that are connected to the gateway. The gateway learns the routes from all these VPCs and channel them back to you via that session. The routes that are learned from the VGW are propagated back up to the other virtual private gateways. It's a one-to-one communication. The only thing that's advertised to your virtual private gateways or your VPCs is the routes learned from your on-premises network. And by doing that, we've now simplified your route tables. So to create a virtual private gateway environment, you first create the gateway, and then associate your VPCs. And once these VPCs are associated, you then create your virtual private interface, or your private virtual interface, sorry, to the gateway. So, what is not possible? What is not possible is I can't route traffic between multiple private virtual interfaces that I've attached to my Direct Connect gateway. Yes, I can attach multiple private virtual interfaces that are all from different geographic regions. Again, Direct Connect gateway is global. So for my Ireland office, I can create a private virtual interface for that office, attach it to my Direct Connect gateway, and now I have access to all the VPCs across the world, just like my Oregon office does. So I can attach multiple. The thing is, I can't route traffic to these different locations via my Direct Connect gateway. It only allows for traffic between a VPC and a specific network. I can't route traffic through my Direct Connect gateway to another VPC in another region. That's where your inter-region VPC peering comes in. I also can't route traffic across a VPN connection. When I say VPN, I mean an IPsec tunnel established between another network and the virtual private gateway of a VPC. All right. What can I do? I can actually route traffic intended for a VPC endpoint service through my Direct Connect, further keeping everything in my private network. what we're doing is reducing the amount of traffic that goes to the internet that doesn't have to go there, right? And giving Direct Connect Gateway this ability further allows you to do that. The thing is, a Direct Connect Gateway only allows access to resources in the account in which it was created. So if you have VPCs that are not in that account, then you have to go the traditional way of creating a private virtual interface to that VPC in another account. You can overcome this limitation by leveraging private links. So you expose that service as just a VPC endpoint service, and then connect to it via your Direct Connect Gateway, regardless of the account that is built in. That's one way of actually overcoming that limitation. Another way is to, again, create a private virtual interface to the VPC. Great. What if you only have IPsec tunnels? You don't have Direct Connect Gateway as yet. Then you would have to actually go the traditional way of connecting these things via a transit VPC environment. That's where you have VPN appliances inside your VPC, and now you're creating IPsec tunnels between those appliances and the virtual private gateway that resides in the VPCs externally. You can actually read more on our transit VPC solution at this link. All right. So, all right. So we've spoken about connecting to VPCs, right? What about connecting to Amazon public space or public services via my Direct Connect in a specific region, but also in multiple AWS regions? How have we simplified that? Once upon a time, you could create a virtual public interface using Direct Connect to any region inside the United States, which means I could connect to S3 even if my Direct Connect public virtual interface was created in Oregon. I could access all public services within the United States. But what about the world? What if I actually wanted to access S3 in Germany, in Ireland, in Asia? How would I do that? How does Amazon actually simplify that? And what we've done is to give it the ability to create a single public interface and then receive all of the Amazon global, receive access to all Amazon public services across the world. Further simplifying, configuring connection between your data center and the broader AWS space. What this means is, once you create a public virtual interface, we advertise to you the routes to all AWS services across the globe. Today, that's 2,000 routes, approximately. But of course, that's going to grow. So from my data center, I can reach any AWS service. I can even reach Amazon.com globally. So if I now have access to all AWS public service space and IP addresses, how then do I narrow that down? I mean, there are clear advantages in actually having that. But what if my route table can't handle all that route? How can I further pare that down? You can do that leveraging BGP community tags. Now, we give you the ability to narrow where we advertise your public IP address space that you give to us. We can advertise it within a single region, or we can take that advertisement and issue it out to all AWS regions. And you do that by specifying these tags. Well, 7224:9100. But we also advertise our routes with BGP community tags for you. So you can basically filter the routes coming into your network. Right? So in conclusion, when should I use what? Right. I recommend using Amazon private links or VPC endpoint services for those applications that don't require SSL offloading, right? Those applications that can live behind a network load balancer that doesn't require UDP, right? Instead of using VPC peering, create your service, attach to a network load balancer, and then advertise that as a VPC endpoint service to your other VPC that exists, but also to other accounts that you may have. I recommend using Direct Connect Gateway to simplify connecting to multiple VPCs within a single account. I also recommend VPC intra and inter-region pairing, but I recommend using these sparingly. And I say that because there is a hard limit on the total number of paired connections that you can actually have. Today it's 125. I recommend using Direct Connect public VIFs with BGP community tags, especially if you don't need all those routes. If you know you only want to connect to a single AWS region, then just create the traditional public interface to that region, or use BGP tags with further configuration. And if you don't have Direct Connect, and you want to communicate, and you want to simplify, communication between many VPCs without using VPC pairing, then you can use the transit VPC. But what I've seen over the years is as customers adopt the cloud and start migrating more applications to the cloud, they start implementing Direct Connect. I would recommend defining success. Before you implement anything within the AWS environment, define what success looks like, because that helps you to actually plan way ahead. And customers who plan ahead become very successful and have less redesign time. So define what success looks like, right? Go as big as you can for your IP space. Thank you very much for coming. I hope this has been helpful, and you're awesome.